molecular rearrangement. So this is our first lecture on molecular rearrangements. In this lecture, we will start with the Favorskii rearrangement. The Favorskii rearrangement, which has been named after the Russian chemist A.Y. Favorskii, is most principally a rearrangement of cyclopropanones and enolizable alpha-haloketones. What happens is that when alpha-haloketones, which are enolizable, or the cyclopropanone derivatives of halogens, they are reacted with a base, they are converted into carboxylic acid derivatives, and such type of conversion of these alpha haloketones into carboxylic acid derivatives is called as Favorskii rearrangement. And when we use cyclic alpha haloketones, then ring contraction may also take place in case of these types of substrates through Favorskii rearrangement. As I have told you, the reaction takes place in presence of a base, and most commonly used base is hydroxide ion, and this hydroxide ion will give us carboxylic acids as the products. But if we use alkoxide base or amine base, then we will get either esters or amides as the product. So depending upon the type of base used, we will get either carboxylic acids as the products or derivatives of carboxylic acids as the product. Now, for example, if we are having alpha dihaloketones, then HX, depending upon the type of halogen present, that will be eliminated to give us alpha beta unsaturated carbonyl compounds. So, depending upon the substrate, we can get the product also. So, if we are using monohaloketones, then we will get carboxylic acids or their derivatives as products. But if we will use alpha dash dihaloketones, then we will get alpha beta unsaturated carbonyl compounds. And how these types of products they are formed, we will see in the next few slides. Now, for example, if this is an open chain alpha haloketone, which is when treated with the base, this will be converted into the corresponding carboxylic acid. Similarly, this is an example of alpha chlorocyclohexanone, and you can see over here that the 6-membered ring ketone is converted into 5-membered carboxylic acid through ring contraction reaction when this is treated with the base. The mechanism of the reaction is like this, that we know that this is the alpha carbon, and any hydrogen present at the alpha carbon will be known as alpha hydrogen, and this alpha hydrogen is very acidic because of the presence of this carbonyl group, because this can be easily removed to give us enolate ion. So what base will do, base will abstract this highly acidic proton present on the alpha carbon, and this will make water will be removed, and we will generate a carbanion at this place. So this type of carbanion is formed, and this carbanion will attack at this carbon to eliminate the halogen atom present, which is also present on the next alpha carbon to the ketone, and we will get this type of cyclopropanone intermediate, and you can see that this is a symmetrical cyclopropanone intermediate which is formed during the first step of the reaction. Then the base will again attack this carbon of the carbonyl, and enolate ion will be formed. This type of this carbon oxygen double bond will become carbon oxygen single bond, and negative charge will be there on the oxygen. Then this pair of electron goes back to oxygen to create the carbon oxygen double bond. Then either this bond or this bond, they will break, this carbon carbon bond or this carbon carbon bond, they will break to give us the this type of ring contracted product. Now you can see over here both this carbon carbon bond and this carbon carbon bond, they are symmetrical and same, either this breaks or this break, we will get the same product. So then this carbon ion will abstract proton from water and we will get our product. So this is how the alpha chlorocyclohexanone is converted into cyclopropanone carboxylic acid as the product. So this is the mechanism of Favorskii rearrangement. Now the mechanism which we have seen in the previous slide was that of cyclic alpha haloketones. But in case of open chain substrate, the mechanism is like this, that in case of open chain also the the hydrogen present at the alpha carbon is acidic, and that will be removed by the hydroxide ion, and we will get this type of enolate ion, which is an open chain enolate ion. And then this carbon oxygen single bond will be converted into double bond, and this pair of electron will attack at this carbon to eliminate the halogen atom, and again we will get a cyclopropanone intermediate, which we have seen in case of cyclic structure also, and then again attacked by the base to give us this type of intermediate, and then breaking of either this bond or this bond. Here also this is a symmetrical structure, so either this bond breaks or this bond breaks, we will get the same product. So this type of carbon ion is formed, and this will take up proton from water, and we will get carboxylic acid as the product. And overall, if you see, halogen was present at this carbon, which I have given a star, and this alpha carbon is also given a star. From here hydrogen is removed, from here halogen is removed, and you can see there is a change of position of these carbons, because when breaking of bond takes place, then change of these positions takes place, and 1,3 carbons, they will become 1,2 carbons in Favorskii rearrangement. Then we will discuss few applications of Favorskii rearrangement, so that the rearrangement will become more clear to you. For example, 2-chlorocyclohexanone, for which you have seen the mechanism also. There we have used sodium hydroxide as a base, and product formed was carboxylic acid. And in place of sodium hydroxide, if we use sodium ethoxide as the base, then the product formed is an ester instead of acid, because here the base which will attack the cyclopropanone intermediate, which is formed by elimination of this proton and this halogen to give us this type of cyclic intermediate, cyclopropanone derivative, then base will attack that cyclopropanone derivative, and here base, instead of hydroxide ion, we are having ethoxide ion. So ethoxide ion will attack this carbon of the carbonyl, and likewise we will get esters as the product instead of carboxylic acid. And you can see that 6-membered ring of the substrate has undergone ring contraction to give us a 5-membered structure. So here the Favorskii rearrangement has led to the formation of esters as well as ring contraction in the product. Then another example is if we take 3-bromo butane 2-one, this one, and here X is bromide, and the product formed will be 2-methyl propanoic acid when this is treated with sodium hydroxide. So we can see over here when this hydroxide ion will abstract proton from this alpha carbon in the first stage, then this carbon ion will attack this carbon and bromide will be eliminated, and we will get this type of cyclopropanone derivative as the intermediate. And now we know that base is to attack this carbon of the carbonyl, and after that a carbon-carbon bond is to be broken. Either this carbon-carbon bond or this carbon-carbon double bond can break. But here you can see that this carbon-carbon bond has a different environment than this carbon-carbon bond. So that means we have to say that preferably which carbon-carbon bond out of these two, either this or this, will break. So in such cases where the cyclopropanone derivative formed as intermediate is an unsymmetrical derivative, then ring opening will take place to give us less substituted carbon. So that means if this bond breaks, then carbon ion formed will be this one, CH2 negative. If this bond breaks, you will get a carbon ion of this type where this carbon will bear the negative charge, and here this will be more substituted carbon. So that is why the breaking of this bond take place, because this will give us a less substituted carbon ion. And less, after the formation of less substituted carbon ion, we will get this as the product. So this is how we can explain that in case of unsymmetrical cyclopropanone derivatives which are formed as intermediate, in what way the carbon-carbon double bond will, carbon-carbon single bond will break, either this bond or this bond. So in general, if we have to say that breaking of cyclopropanone derivative will take place in such a way that less substituted carbon ion will be formed, and that carbon ion will take up H positive ions from water and give us carboxylic acid as the product. Then if we use amines as the base, then the product formed through Favorskii rearrangement in case of alpha-haloketones, they will be amides. So for example, if we are having this type of alpha-bromoketones and this secondary amine is used as the base, then the product formed will be this one. This type of amide will be formed. In the first instance, this base will abstract this alpha proton from this alpha carbon, and carbon ion will be generated at this place, and this carbon ion will be more stable because of the presence of this phenyl group, benzylic carbon ion, and this carbon ion then will attack this carbon and bromide will be eliminated to give us a cyclopropanone derivative as the intermediate, and then that cyclopropanone derivative will undergo breaking of the carbon-carbon bond by attack of the base to give us this type of amide as the product. Some more examples. So as I have told you that alpha-alpha dihaloketones, alpha-alpha means if both the halogens they are present on the same carbon. Alpha-alpha dash means when they are present on the different carbon. One halogen is present at this alpha carbon and other halogen is present at this alpha carbon. So these alpha carbons, they are different, then we say alpha alpha dash dihalooketones. But if both the bromides, they are present on the same carbon, we say alpha alpha dihalooketones. So either these or these, they rearrange to give us alpha beta unsaturated carboxylic acids or their derivatives, depending upon the type of base which we use. For example, here we have used sodium ethoxide. So that means we will get alpha beta unsaturated esters as the product. But if we will use sodium hydroxide over here, then the product formed will be carboxylic acids. So depending upon the type of base used, we will get alpha beta unsaturated carboxylic acid or their derivatives as the product. So for example, in this case alpha alpha dash dibromoketone. So in the first step we will get a carbanion formed, and then that carbanion will eliminate the bromo at this place, and we will get this type of unsymmetrical cyclopropanone derivative, and then this will interact with the base will attack this carbon, and we will get this type of intermediate, and then this will undergo elimination instead of. So now there is not the possibility that either this bond can break or this bond can break. Here that path will be taken up where elimination of this bromide can take place. So this will go to this place and this bond will break and bromide will be eliminated, and we will get the more stable product in the form of alpha beta unsaturated esters as the. Now for example, in case of alpha alpha dash dihaloketones, they can be converted into carboxylic acids also, as I have told you that if we will use base as sodium hydroxide, then we will get carboxylic acids as the derivative. So when Favorskii rearrangement take place, in this case we will get these types of carboxylic acids, and these carboxylic acids, they will undergo decarboxylation to give us ketones as the product. So when alpha alpha dash dihaloketones on Favorskii rearrangement, they are converted into ketones through carboxylic acid, then this reaction is known as Wallich reaction or Wallich degradation. So basically an additional step of oxidative decarboxylation takes place. Similarly, we can synthesize cubane carboxylic acids through Favorskii rearrangement, and the same thing if we are having alpha bromoketones as the starting materials through Favorskii rearrangement in presence of sodium or potassium hydroxide, they can be converted into cubane carboxylic acid, and mechanism of the reaction is same as we have discussed in the previous slides. Then as I told you that non-enolizable alpha haloketones, they undergo quasi-Faverskii rearrangement instead of pure Faverskii rearrangement in the presence of bases. So here what happens is, for example, this is the synthesis of a powerful analgesic, that is painkiller, pethidine, which is also known as damirol or mapridine. So this is the structure of damirol. So what happens is, this is in fact the substrate is alpha chloroketone, and when this is reacted with hydroxide ions, we know that this will undergo this halogen will be removed in the first instance, and this phenyl will be shifted to this place, and hydroxide will attack at this carbonyl instead of formation of carbanion, which is formed as a first step in the Favorskii rearrangement. But here the base will attack at the carbon of the carbonyl instead of formation of carbonyl. So in the first instance, this is converted into this type of carboxylic acid, and when this is reacted with HCl and ethanol, we know that this is a tertiary amine. This will be converted into quaternary ammonium salts, and this is the structure for the analgesic or painkiller Demerol. So mechanism for formation of this reaction, that here no cyclopropanone intermediate is formed, as we have seen in case of Favorskii rearrangement. So that is why this is an abnormal Favorskii rearrangement, which is called as quasi-Faverskii rearrangement. So here the base will attack the carbon of the carbonyl in the first step, and we will generate a enol. The carbanion will reduce this double bond into a single bond, and we will get this type of negative charge on oxygen. When this will come back, then migration of this phenyl group will take place to eliminate this halogenator, and 1 to phenyl shift will lead to the formation of this type of product, which is this second step. And then through this step we will be able to synthesize the Demerol, that is analgesic or drug which is used for painkiller, used as painkiller. And then a few more examples of non-enolizable alpha bromoketones which undergo quasi-Faverskii rearrangement. So these types of alpha bromoketones, 2-bromo-bicyclo, 2,2,1 heptyl phenyl methanol. So when this is reacted with N-lithium phenyl as the base, what will happen? This base will attack the carbon of the carbonyl directly instead of forming a cyclopropanone derivative, and we will get this type of intermediate. Then this will go to this place to again generate the carbon oxygen double bond, and then this phenyl will migrate to this place and bromide will be eliminated. So here again a migration of the phenyl group take place. 1,2 phenyl migration leads to the formation of this type of product, which we say is formed by quasi-Faverskii rearrangement. So this type of bicyclo carboxamides, they are formed as the product. Then another example of non-enolizable alpha bromo bicycloketone. See this type. This is the substrate. 1-bromo bicyclo 331 nonane 9-one. So when this is reacted with mercuric acetate in ethyl oxide, this act as a base, and ethoxide in the present ethoxide from ethanol attacks this in presence of mercuric oxide, and we will get this type of intermediate form. Then here when this comes back to this place, then this carbon-carbon bond migrates to this position for the elimination of this bromide. So here 1,2 alkyl shift take place to give us this type of product. So this is again an example of quasi-Faverskii rearrangement, and in all these types of reactions the cyclopropanone derivative which is formed as intermediate in the Faverskii rearrangement, that is not formed, instead there is a migration of either phenyl group or alkyl group to give us these types of stable products. Then another is photo-Favorskii rearrangement reactions. So here the reaction takes place under photochemical conditions. So when these phosphate esters, they react with these types of phenacyl bromide derivatives, then we will get first these phosphate esters, they react with phenacyl bromides with the elimination of this bromide ion from here, and we will get phosphate esters as the intermediate. And then these phosphate esters, they will undergo hydrolysis to give us these types of phenolic carboxylic acids as the product. And this reaction proceeds through a triplet diradical like this. In the first instance, this type of diradical is formed. H goes from here, a radical is formed at this place, and then this bond breaks to generate a free radical. This diradical, triplet diradical, then gets converted into diones spiro intermediate B. Here what happens is that this CH2 attacks this ring to form a cyclopropanone derivative, and this type of spirodione is formed, and then this spirodione undergo hydrolysis to give us this type of product. Then another example of photo-Favorskii rearrangement is found in these types of substrates. These are again phenacyl chlorides. Only difference is that instead of phenolic, they are substituted by alkyl side chain. So if we are having 4-ethyl 4-ethyl phenacyl chloride and this undergoes photochemical reaction, this will undergo homolysis by breaking of this carbon halogen bond to give us this type of radical, and then there is electron transfer from this radical. This electron is transferred to this chloride free radical, and this will become chloride negative, and this carbon will become a carbonyl ion. So carbocation is formed like this, and this will form an anion. And after this 1 to aryl migration, this whole aryl group will migrate to this position because the carbon ion formed will be more stable, and this carbocation through 1 to aryl migration will change into this carbocation acylamine, and this will undergo hydrolysis to give us carboxylic acids as the product. So this type of rearrangement, because this is taking place under photochemical conditions, is called as photo-Favorskii rearrangement. So these are some of the references which have been used to prepare this reaction, that is Favorskii rearrangement. Thank you very much.